Okay, in this lecture we're going to discuss the data movement instructions. Instructions that are used to move a data from a place to another place. Could be from an internal register to another internal register, or between memory and internal register. These kind of instructions do not affect the flags. They do not perform any arithmetic or logical operations, so the flags are kept intact. They do not affect the flag. Okay, the form of this kind of instruction is the most famous form is move, M-O-V, which is used to move a data from a place to another place. It can be used to transfer a byte or a word among the places we mentioned, memory, register, or I/O device. Okay, the instruction looks like this. The mnemonic code is MOV, assembly code, which means we are going to move a data from a source S to a destination D. So the content of a destination, the content of the source goes to the destination. The content of the source goes to a destination. So we're copying the data from the source to a destination without affecting the data in the source. So after executing this instruction, the data in the source will be kept as is, and as we previously mentioned, it does not affect the flag bits. These operands take different forms. The operands used with the move, you could move data from an accumulator to memory, memory to accumulator, register to register, and so on. So these are the operands used for the source, and these are the operands used for destination. Okay. And there are certain rules you have to follow in using this move instruction. What are these rules? First, you're not allowed to move a data from a memory location to another memory location directly. You have to go through some internal registers. So you do not take a data from a memory location to another memory location. You have to do this through some of the internal registers. And as well, you cannot switch data between segment registers. All right, you don't have to move, or you're not allowed to move a data from a segment register to another segment register. Your memory segments will get messed up, and the code will get mixed with the data and so on, and the stack and extra segments will lose their meanings. All right. And one more thing, your source and destination have to be of the same size. So you move an 8-bit data into an 8-bit register, a 16 bits of data into a 16-bit register. So the both source and destination have to be of the same size. Good. The first two instructions to be used to move a data inside a stack segment register, which has 64 bytes, is push and pop. And the stack segment register starts at the address stored in the stack segment register. So the stack memory segment has 64K of bytes. Each byte is addressed. The first address of a byte inside your stack memory segment, is stored in your stack segment register. Okay, and there is a pointer helps you getting to some memory location inside your stack, which is known by stack pointer. And it is used to point to the top of your stack. And SS is used to point to the bottom of your stack memory segment, to the starting address. Okay, and we have 4 instructions in moving to be used in moving data from your stack memory segment to your memory of the device. So these are push. You push a data inside your stack memory segment. You get it back by pop. You can push your flag register, you can get it back by pop. So you can push a 16-bit of data inside your stack memory segment by push. You can get it back by pop, and you can as well store your flag bits inside your stack memory segment by push F, and you get it back by pop F. Okay, the instructions used to store data into stacks and brings data back from the stack is push and pop. So these push and pop are used in storing data into the stack and getting back the data from the stack. For example, push. It push 16 bits of data inside the stack, a word into the stack. And you have to specify only the source from which the 16 bit is taken. So this is the format. It takes the 16 bits from your source, store them into the stack. Where in the stack? Into a location pointed to by SCP. So by writing push S, this instruction will take 16 bits from your source, store them into the stack. Where in the stack? By in locations pointed to by SCP. And you get it back by pubd. You have to specify only a destination with pub. This will take 16 bits of data from the stack. These 16 bits of data are pointed to by SCP. You take these 16 bits, put them back into whatever destination you wish to store your data in. And you do the same with the flag register. You push F, okay, takes the flags from your flag register, store them into the stack again in a place pointed to by SCP. You bring back your flag bits from the stack by pop F. So now you get it back to flags. Good. The operand used with the push and pop could be register, 16-bit register, could be 16 bits of memory, could be segment register, 16 bits, or flag register. They are all of a word length, 16 bits. So dealing with the stack, you send in 16 bits and you get back 16 bits at a time. Okay. Okay, another data movement instruction is the load effective address, and they come in three forms: LEA, LDS, LES. And here are the differences between or among these three. LEA, this is load effective address. It takes the effective address, stores it into a 16-bit register. So the effective address is stored in a 16-bit register. LDS deals with 32 bits of data. Okay, 32 bits. All right, so you have 32 bits from your memory. The least significant 16 bits goes to a 16-bit register, and the most significant 16 bits goes to a DS, which means this instruction is used whenever you need to change your currently active data memory segment, because you are going to load a value, a new value inside your DS, which means you are switching to a new data memory segment. And same thing with LES, except that you are using here a new extra memory segment. It has to deal as well with 32 bits of data. The least significant 16 bits goes to a register, and the most significant 16 bits goes to ES. Again, you are changing your currently active ES. Okay, the load effective address. As we mentioned, it used to store the effective address in a 16-bit register. So what is the difference between load effective address and move? Here is the difference. For this instruction, load effective address bx comma di as an effective address, it takes the effective address, which means the content of di, not the data pointed to by di, place it into bx. So after executing this, the value inside di would be inside your bx, and bx is equal to di. To do this with the move, you just say, if you use the same format with move, it doesn't give you the same thing. Here, the data pointed to by di is stored in bx. So the result is not bx equal to di. If you need your bx equal to di using the move instruction, you would have to do this. Move, move, move bx comma di, not di inside square brackets, which means the address. So load effective address bx comma di between square brackets is equivalent to move bx comma di without any brackets. Here is an example. Load effective address cx.di. What this instruction does, it takes the content of di, which is the address, loaded to cx, not the data pointed to by di, the content of di by itself. So before execution, if this is the value of your cx and this is the value of your di, after executing, your cx would contain this data. Okay, here you are. And the will keep the data inside it. Another example. Now your cx is going to be loaded with the value inside bx plus the value inside your di, not the data pointed to by bx plus di. So if this is the value inside your bx and this is the value inside your di, after executing this instruction, your cx will contain 3000. Okay, the addition of bx and di. Okay, and if this is the value inside your bx and di, if you add these together, you would get a carry 1, and you check the value inside your cx, it would be 0f00. Now comes LDS and LES. Again, they deal with 32 bits of data. With LDS, the least significant 16 bits goes to a 16-bit register, and the most significant 16 bits goes to DS, while here the most significant 16 bits goes to ES. Good. Okay. And dealing with 32 bits, we don't have 32-bit registers, so we have always to go to memory to get 4 bytes of memory. Example. If we execute this LDS SI, this. So this now is an address. You go to the physical address by multiplying the value inside the S by 10, add this address. Now you go to some location in your memory, and you have to get 3 more locations above this memory in order to form a 32 bits. The lowest 16 bits should go to SI, and the highest 16 bits should go to DS. Let's see this. This is your DS, this is your SI. Definitely this value is going to be changed, but we have to locate first 4 locations of memory. The first one is given by DS times 10, ds times 10 plus 200, which is 12,200. So this is the first. So you get 3 more locations up. Now, the least significant bits, which is 0020, the least significant 16 bits should go to SI. The most significant 16 bits should go to your DS. Here you are. This is your physical address. DS times 10 plus 200. After execution, your SI is going to have or to get 0020 of data, and your DS will get 1300 as a data. Good. Example 2 now goes to LES. Same thing. DS times 10 plus DI gets you an address inside your memory location. You have to go 1, 2, 3 locations up, and you take the lowest 16 bits, store them in BX, the high 16 bits, store them in DS. Here you are. This is your physical address. You go to memory location. This is your first. You get 3 locations up. The least significant 6F2A, 6F2A goes to your BX. The most significant 8930 goes to ES. And here you are. After execution, this is the value inside your BX, and this is the value inside your ES. Okay, another type of data movement instruction is the string data transfer. String means we're dealing with a block of data or an array of data. Okay, so these instructions are designed for you to ease your life when dealing with array of data or blocks of data. By a single instruction, you can move along an array of data. These are load, string, store string, or move string. We're loading a string of data, a block of data, storing a block of data, or moving a block of data. Good. So we're dealing now with a block or an array of bytes or words. And in dealing with blocks of data, we have to specify where to take a data from, where is the source, and we use SI to point to the source of data. DI now is dedicated to point to the destination. Then we have to use the D flag, because in dealing with blocks of data, you can move forward by auto-incrementing the address or backward by auto-decrement the address. This is done by storing either a 0 in the D flag when we need to move forward, or a 1 inside the D flag when we need to move backward. Okay, this table shows you these instructions. For example, move S. Okay, move string. Let's take this. Move a string, a block of data, a byte by byte. What this does is this. It takes the content of DS, multiplies by 10, added to the content of SI. It gets a physical address. The content of this physical address is moved to some memory location inside your ES. This memory location is determined by physically by multiplying the value of ES by 0, add the content of DI to it, we get a memory location So you are moving a data, an element of data from DS at this specific location to ES at this specific location. And if you are moving a byte by byte forward or backward, you have to increment your SI and DI by 1. And since you've chosen to write move SB, so you are moving a byte by byte. So you have to add one more byte forward, or to subtract one more byte if you're moving backward. But if you are moving your data word by word, you have to add or subtract 2, because you're taking 2 bytes at a time. Same thing with load S. Load S, it takes a value from a physical location, physical memory location, 0.22 by ds times 10 plus ss. So this is the content of this memory location. It stores it in ex if it's a byte, if el if it's a byte, and ex if it is a word. And you have to add or subtract 1 if you're dealing with bytes of memory, or add or subtract 2 if you're dealing with words of memory. And you do the opposite by store. You take a data from AL or AX, place it back into your ES using DI as a pointer, okay, and you increment it by 1 or decrement it by 1 if you're moving a byte by byte, or 2 if you're moving a word by word. Good. Better be explained by an example. Okay. If load string W, so you are moving a word by word. This is your DS and this is your SI. So now your source location is determined. Multiply DS by 10, add to it SI. You go to a memory location. Your value of AX, whatever the value inside this, but the direction flag bit is 0. So when you go to some memory location to move up, not down, to get to the other memory location to get a word of data. Good. So multiplying this by 10, adding this to it will get you here. You have to go one more place up to get a word of data. Low in low and high in high. This is your word of data. This is to be placed inside your AX, because load takes data from memory to AX or AL. Here you are. After execution, this is the value inside your AX. Good. And your SI has moved 2 places up, because you've taken now these 2 places and your SI goes to here. Okay. And for your string data movement instruction to be effective, they designed a repeat suffix to enable you use these string instruction through your blocks of data. So we have a prefix repeat. Here you are. This is move or store. You prefix it by rep, which means you repeat this instruction. How many times do you repeat it? You repeat it as many times as the value inside your CX. So you repeat it till the value inside your CX is 0. Better again be explained by an example. And here is a program. Good. What you do by this, what does this instruction do? Well, you have a block of data named list1. You will take the first 16 bits, the least significant 16 bits from your list1, place them into the I, and the most significant 16 bits into your ES. So you are pointed now to some location inside your ES. This is your ES. Okay, this is the new ES, and here is your value of DI. Okay, good. So it loads DI and ES by the first address and the destination list 1, the first address. Good. You do the same thing by list 2. You go to your new data segment, you're pointed to a location by SI. So now you've opened up two memory segments, ES and DS. The source pointer is used with DS, the destination pointer is used with DI. Good. Now you clear your direction flag bit, indicating that you are going to move up. You are going to move up, not down. You are going to increment your address by 1. And you're going to do this 100 times. Now, repeat, move SB, which means you're going to go to the place pointed to by SI in your source, take a byte, not a word, move it to your ES, to a location pointed to by DI. And you do this 100 times, which means this code is going to move 100 bytes of memory, 100 bytes of data from your DS to your ES. This is what it does. Or from list 2 to list 1. 100 bytes from DS list 2 to ES list 1. You can do this in twice as much faster by, okay, this is another example. Okay, another example. We have a block of data named the buffer in ES, and we are loading DI by the first 16 bits and ES by the second 16 bits in your buffer. Okay, looks like we're going to do something 10 times. And we're going to move forward. We're clearing the direction flag bit. Okay. We are going to place 0 in AL. We are going to store byte by byte whatever value inside AL into your buffer. Where in the buffer? Where in the buffer? Starting in a location pointed to by DI and moving forward 10 location up. Moving forward 10 location up. Which means what? By repeating this, we are going to clear the first 10 bytes in the buffer. In the buffer. The piece of memory inside your extra memory segment named the buffer. We're going to start at DI, moving 10 locations up and place 0 inside each location, which meaning we are clearing the first 10 memory locations. Okay, so we are doing what? Clearing the first 10 memory location in buffer. And we can do this twice as much faster by storing here 5. And instead of moving a byte by byte, we can move a word by word, which looks like this. Same thing, except that we store 5 in CX and we repeat moving a word by word, and we store 0 in AX, which does the same thing, which is this, which does the same thing, clears the 10 memory locations, 10 bytes, whose starting address is buffer. Okay, another instructions which are used to move data. These are certain miscellaneous data transfer function. Okay, these are exchange, load flag, store flag, in and out, translate. Okay, so these are 4 miscellaneous data transfer instructions. Okay, the first instruction we're going to discuss is the exchange instruction. What does this instruction do is it exchanges the data from a register to a register in a memory. So it switches the data. If you have a data inside the register 1, R1, and another register R2, it takes whatever inside R1, places into R2, and does the opposite with R2, takes the data from R2, places into R1. And the same thing with the memory locations. So it takes the data from a destination, place it into a source, and the data from a source, place it into a destination. The operands used for the source, 16-bit register or a register. So you take register, 16-bit to accumulator, a register to memory, register to a register. For example, if this is the value inside your BX, and this is the value inside your DS, and a memory location pointed to by sum, this is the offset of the sum, and inside this memory location, this data is stored. So this memory location points to not a single byte, but to 2 bytes. DS times 10 plus this address gives you the memory location 34 and the memory location 35. And in 34, the low 87 is stored. In 35, 1E is stored. Okay. If we are executing this code, it takes the value inside BX, which is 11AA, places into sum. So the memory locations here are going to change. The low byte will contain AA, and the high byte will contain 1. And 1E87 is going to be placed into BX. So after execution, BX will contain 1E87, and sum will contain in its 35 byte, the highest byte will contain 1, and the lower byte will contain AA. Here you are. This is your physical address. After execution, this is the value of your BX, and this is the value of your sum, the memory location labeled sum. Good. Load AH with F, store AH in F. Good. It transfers the data, the flag bits, flag byte, into AH register, the higher portion of your AX. And these instructions which are used to do this. Load FAH, it takes a flag into AH. The flag bits are stored in AH with load F into AH. Store AH into F, it takes whatever values inside AH, store it in the flag. For example, let's say this program. Here, we are storing 0 into AL, clearing AL. Load F into AH. So it takes the value of the flags, place it inside AH. Now exchange AL with AH. So zeros are stored now in AH, and flags are stored in AL. Exchange the data between AH and AL. Store AH into flag. So the value now in AH is zeros, store it into flag. So this definitely will clear the flags, will make all flag bits zeros. So store H into the flags. So this program clears all flag bits. Sometimes you need to clear the flag bits before executing some portion of a code, and you would like to know whether this portion is producing positive or negative number, producing a 0, your parity flag or your carry flag. In and out. These are used with output devices, I/O devices. In, you're bringing in data from outside to your processor using an input port. Out, you're sending out data from your processor to the outside world through some devices, input device, output device. Okay, this transfer goes through either AL if you are transferring a byte by byte, or AX if you are transferring a word by word. And use the port addressing mode to refer to the device you're getting data from or you're sending data out. The last instruction is the translate instruction. They are very useful in dealing with lookup table. And this is useful in transferring bits, binary coded decimal, if you are representing the decimal numbers from 0 to 9 binary, and you would like to display this on a 7-segment display as digital numbers. You store the 10 values inside a table. We call it a lookup table. So you add here the first, second, third data, which are used to display 0, 1, 2 on your 7-segment display. How would you do this? Okay. When you write this instruction, translate, and you give the source table, what this instruction does, it goes to the data segment, get the physical address, add to it the content of AL, and whatever byte is placed here is sent to AL. Okay? Then, if you would like to send this out, you say out AL. And again, it adds the content of AL to the content of BX, all right, register, to form a memory address in the data segment, because you have to add this to DS times 10. For example, converting binary coded decimal into 7-segment display. Good. If you have your lookup table stored beginning at this location in a data memory segment whose starting address is this, and we need to write a program to convert values from lookup table into the 7-segment code, or the 7-segment code to be used to display whatever decimal number through your 7-segment LEDs. Okay. Here, table is pointed to by BX. So the first data in your table is pointed to now by BX. Initializes BX by the offset address of your table. Now we're moving 5 hexadecimally into AL. Probably would like to display the decimal digit 5 into your 7-segment display. This is why we placed 5 in AL. Okay, good. Then translate. What this instruction does is this. It will go to your DS memory location, where in your data memory segment it will get a data from, it goes first to BX, which gives you the starting address of the table. Then add 5 locations according to AL. Then it takes the byte inside this memory location. So the memory location, the physical address is calculated as such. DS times 10 plus BX plus 5. So AL will be loaded by the 7-segment code equivalent to 5 from here. Okay, this is the byte equivalent to 5. And this is the physical address, DS times 10, add to it BX, add to it whatever value inside your AL. If you went there to this memory location, you will find these data stored hexadecimally 6D and binary as such. So if you send this to a 7-segment display, this is your LED A, B, C, D, E, F. So your A will be turned on, B off, C on, D on, E off, and so on. Finally, you will get this number displayed in your 7-segment display, which is 5. The same number is stored in your AL. If you'd like to store, if you'd like to display 6, you write here 06. If you'd like to display 0, you write here 00, and so on. Okay. Hopefully the idea is clear now and the material is understandable, and this very important and useful instruction has been well understood. Translate. Okay.